Let me start by joining the speakers and some of the chairperson in thanking the organizers for this wonderful job they did and they are still doing. And we're happy to have Gabriel Wong from Oxford, who's going to talk about 3D gravity as a random ensemble.
Well, thank you to the organizers for inviting me to give this talk. This is work to appear soon with Dan Jeffress and Lisa Rosenberg. I want to begin with some general comments about gravity and averaging. There are two types of averaging. One is over UV microstates. This is due to black hole solutions, whose horizon area gives us a density of states that describes this dense spectrum of black hole microstates. This is continuous because it's averaged over a high energy window, and in ADS3, it corresponds to the Carty density of the dual CFT. On the other hand, gravity also computes ensemble averages. This is because of wormholes. This is manifest in geometries that have a disconnected boundary. The gravity path integral instructs us to sum over all bulk topologies that end on these boundaries. There's a disconnected contribution, but also a connected one with the wormhole. There is an apparent tension with the dual quantum mechanical system, which tells us just to compute the product of the partition functions corresponding to the disconnected part. We've come to understand that the inclusion of these wormhole topologies should be viewed as providing a coarse-grained description in terms of an ensemble of quantum systems. So there's really an average of partition functions. So there should be a long list of citations here, but I'll defer to Monday's review talk for those references. These two types of coarse graining are related. For a chaotic system like a black hole, averaging over a high energy window is indistinguishable from averaging over an ensemble. Now, just like in statistical physics, the ensemble interpretation of quantum gravity provides the best description of a system given a set of constraints. For instance, the microcanonical ensemble maximizes entropy subject to the constraint of fixed energy. Similarly, a random matrix model describing a random Hamiltonian H is the maximum entropy ensemble for a given average density of states. This is because the average density of states just uniquely determines the potential for the matrix integral. Now, Sash, Schenker, and Stanford showed that two-dimensional JT gravity is equivalent to a double-scaled matrix model. So this suggests that JT itself is a maximum ignorance ensemble. It has as its inputs just the disk, the path integral on a disk, and a path integral on a cylinder. And in particular, the cylinder is going to determine for us the eigenvalue statistics associated to the symmetry class of the ensemble. Now, given these two inputs, the gravity path integral on 2D geometries is completely determined. And the reason is that we can take any 2D surface like this one, and break it up into little pieces. And topological recursion will tell us how to compute each little piece in terms of these two inputs. So in this talk, I want to consider generalization of SSS, in which we study an ensemble of CFT2s due to ADS3 gravity. CFT2 data is given by a dilatation operator, delta S, that's graded by spin, and the OP coefficients. Now, assuming integer spins, that gives us a set of random matrices indexed by the integer, and a random tensor with 3 indices. Now, the new ingredient compared to SSS is this random data satisfies locality constraints given by the modular bootstrap. This is generated by the 4-point crossing equation on the sphere written here, and also by torus 0 and 1 point modular invariance. We'll argue that the sum of the topologies in ADS3 is producing the maximum ignorance ensemble consistent with this modular bootstrap. Now, unfortunately, I won't be solving any bootstrap equations today because I'll be really discussing an ensemble of approximate CFTs, so the bootstrap equations are only approximately satisfied. So let me first explain that and then move on to explain the rest of the model. An ensemble of exact CFT2s would have a potential that's defined by the Carty density, and a delta function that implements the bootstrap constraints. So this Z0 will be the partition function. Now, for irrational CFTs with only Virasoro symmetry, we don't know how to impose these constraints. So following Bellin, Debord, Jeffress, Naik, and Sonner, we'll relax these constraints by smearing the delta function with a parameter we're going to call h bar. So in this deformed sort of partition function, we have a new term here is a constraint squared potential. By definition, is going to be minimized on the solutions of the bootstrap. This integral defines an ensemble of approximate CFTs with this h-bar parameter parameterizing the violation of the bootstrap. Now, when h-bar is 0, this integral should localize to exact CFTs. So computing this integral for finite h-bar and then taking it h-bar to 0 should teach us something about the space of exact CFTs. We'll first define this ensemble as an integral over finite matrix and finite matrices by truncating to n primaries, and then take a double scaling limit of delta S that sends n to infinity. A priori, we should be taking h-bar going to 0 first at fixed central charge, but we'll organize the Feynman diagrams of the ensemble into e to the minus c expansion, and then take h-bar going to 0 later. We'll argue that this e to the minus c expansion actually reproduces the topological expansion of 3D gravity. So here's a very brief summary. For the insertions of the density, it looks very much like SSS, but with a circle attached. So there's sort of a sum over two manifolds, but we have to attach sort of a hidden circle to it. This circle corresponds to the insertion of a single copy of rho, but now it's a torus insertion, a torus boundary. We have also another observable, the OP coefficient, and inserting it corresponds to putting in a sphere with 3 punctures. In the bulk, there will be multi-boundary wormholes that connect these two spheres with Wilson lines propagating in the bulk. And finally, an interesting aspect of the model is that when we sum over the indices of Cijk, that becomes an insertion we can put in the matrix integral, because a sum over the indices is sum over the CFT spectrum, and that produces surgery on these manifolds. Now, our work has some overlap with many recent papers on 3D gravity, but I think the nice feature is it unifies many of the ingredients that have been discussed in recent years. I want to give a flow chart for the rest of the talk because there's going to be quite a few details. But the main idea is I want to take this maximum ignorance ensemble, input a few simple pieces of data, and then spit out a gravity path integral that sums over topologies. For the tensor model part, you will only need an inner product to take the square of the 4-point crossing equation. But for the matrix part, we'll also need the analog of the cylinder and the disk. So let's start with the easier part, which is the tensor model and its relation to Virasoro TQFT. So the 4-point crossing equation should be viewed as a vanishing of a vector here. So what we need is an inner product to take the square of this vector. We'll use the fact that the space of Virasoro conformal blocks form a Hilbert space equipped with a Valinde inner product and a representation of crossing. The Valinde inner product is very simple on the 4-puncture sphere. It just says that the S-channel blocks are orthonormal up to this modular S matrix element in the denominator. And the overlaps of the S and T channels just give you the Virasoro 6J symbol, which is just the F matrix, the fusion matrix of Virasoro algebra. Now, the inner product combined with the cross representation of crossing is the Hilbert space structure of Virasoro TQFT. When we square the 4-point crossing equation, we get a quartic potential with 4 Cijks. This is the diagonal term and the cross term. It's useful to represent these terms with graphs. The first one is a pillow graph that represents this diagonal term. Each junction of the pillow is corresponding to a Cijk. Each edge corresponds to an index, and the way the edge connect is exactly the way the indices contract. In fact, this pillow graph is what you get by taking the S matrix overlap and gluing along the external endpoints here. Similarly, for the cross term, we get the contraction pattern of a 6J, of a tetrahedral graph. We're going to call it just a 6J graph. And that comes from the gluing together this overlap of the S and T channels. There's a kinetic term hiding inside this potential. It comes from a special case of the 6J, in which you set one of the edges to be identity. And then you just get 2 junctions which correspond to 2 Cijks, and that gives you the kinetic term. We can define triple-line Feynman rules for this tensor model. There are generalization of the double-line Etouffé diagrams. They really come from just removing the junctions from the graph I showed earlier. So for example, here we have a triple-line propagator that you get by removing the vertices of the data graph. There is a pillow and a 6J pattern of lines. Once we remove the corners, we can now connect them with triple-line propagators. We can interpret these diagrams in a 3D gravity interpretation as multi-boundary wormholes with Wilson lines inserted. So for example, here, this propagator becomes an S2 times interval manifold, but with 3 Wilson lines inserted, and with the boundary being punctured spheres. Similarly, there's a 4-boundary wormhole here with a pillow pattern and another 4-boundary wormhole with a 6J pattern. These all come from Wilson line networks inside 3-sphere. The Wilson line network is the graph that we showed earlier, but with the solid ball removed around the junctions. When we do the Feynman diagrams, the rules tell us to glue together the pillow and the 6J, and that gives us sum over 3 manifolds. If we fixed a manifold, we find that these Feynman rules agree with 3D gravity as defined by 2 copies of Virasoro TQFT. That shouldn't be too surprising because we actually inputted the inner product of Virasoro TQFT as well as the crossing kernel. Now I want to explain the matrix and how it implements SL2Z modular invariance. Now remember, for the matrix, we have to introduce 2 extra inputs, which is the analog of the cylinder and the disk. So the cylinder is what we'll start with. It actually tells us about the symmetry class of the ensemble. Our random Hamiltonians, delta S, actually correspond to the GOE ensemble. This is because of CPT symmetry, which is an anti-unitary symmetry that squares to 1 for integer spin. And the GOE measure exponentiates to this van der Waals potential, which has a logarithmic repulsion between the eigenvalues, which are just the conformal dimensions, with this exponent 1 identifying it as a GOE. Now, the cylinder contribution to this 2-point spectral density is exactly just the inverse of this van der Waals. The reason is just because the 2-point spectral density is like the propagator for rho, but the connected term for rho is exactly the van der Waals kernel, so the propagator is just its inverse. Remarkably, this inverse van der Waals agrees with the 3D gravity path integral computed by Kotler and Jensen a few years ago, but with an extra factor of 2 due to some extra wormholes you need to get agreement with the GOE ensemble. Now the disk density for our random matrix is given by the Carli formula. It's a product of Virasoro S matrix elements, which I've written here in terms of the left and right moving conformal dimensions. But in terms of the eigenvalues of our delta S, they're related by these formulas, and the eigenvalue density actually is shifted by S. Now I want to explain this picture I drew here of the solid torus. This is supposed to be the solid torus that describes BTC black hole. The partition function of a BTC black hole is just given by a product of 2 Virasoro characters in the vacuum sector, but it's in a particular channel that corresponds to filling in this green disk where the time circle shrinks. The modular S matrix element is just the matrix that relates the character in one channel with the characters in the opposite channel, which would fill in the spatial circle. Now, in this formula, H and H bar are decoupled. So our density of states is not quite the density of states of BTC black hole, because the integer quantization of spin couples the left and right moving sectors. So we're going to decouple left and right by first trivially rewriting the sum over integer spins as an integral over integer spins, integral over continuous spins, multiplied by direct delta comb. But in the partition function, we're going to insert this identity while also interchanging the summation and integration. So for each fixed n, we have a continuous integral over spins, and now left and right decoupled. But that has caused us a phase. But this phase has a nice interpretation. It is exactly what you get by doing a T transformation. That would mean that sort of a different cycle along this torus will contract. So now we have the ingredients we need to talk about the constraint squared potential. I want to start by saying again that the CFT partition function really should be thought of as a vector. This is just because the partition function is a sum of products of various serial characters, which I've written as these cats over here. And that forms a Hilbert space. Now, if we had an inner product, we can define a constraint square potential in the following way. 1 minus s times z is 1 minus s times z vanishing is the statement of modular invariance. Here, when I say s, I really mean 2 copies of s, but I've just simplified the notation. So if we square 1 minus s times z, then that gives us a constraint square potential. Now, this is a simple observation here. This is a double trace potential, by which I just mean there's 2 sums over the spectrum. Now, when we expand in powers of this potential inside our partition function, we get a vertex we can insert into our diagrams. So here we have a particular diagram in which there are these 2 holes here, which I've connected with the propagator K inverse. This is a torus wormhole. But once we introduce this vertex, we can also sort of interrupt this torus propagation with a vertex insertion. And now we want to find the appropriate sort of gravity inner product to define Vs. It turns out it's not the one defined by TQFT, and I want to explain in some detail why this is true. It turns out the right answer for the gravity inner product is just the GOE Vandermonde I called K earlier, which we should now view as some kind of operator acting on this Hilbert space of versorial characters. Let me explain this more by just repeating the formula for the 2-point function of rho. We'll read the kernel of K inverse as this kind of matrix element. And because it corresponds to the torus wormhole, it should be a propagator. It's a propagator on the torus that evolves it in time. But 3D gravity is topological. So this propagator should just be the identity. Now, why does it look complicated? K inverse here is really giving the resolution of identity, but in a non-orthogonal basis. When the basis is non-orthogonal, the matrix elements of the identity is actually the inverse metric. That makes K the metric itself on the space of characters. This non-orthogonality has a geometrical origin. It comes from the gauging of the bulk mapping class group. In other words, if I take this torus and I try to produce it by gluing it along a bulk slice, gravity gauges the Dane twist I can make along this dotted line, which is just a 2-pi twist, or 2-pi translation along either of the 2 circles of the torus. This gauging makes the versorial characters not orthogonal. But VTQFT would have treated these characters as orthogonal. So VTQFT actually has different random matrix statistics than gravity. Now, we have all the ingredients to kind of summarize what the matrix model does for us. Before we added this potential Vs, we have sort of a simple set of 3 manifolds we get from the genus expansion of the double-scaled matrices delta S. The expansion parameter is the level spacing, which goes like e to the minus c because of the Carty density. And it just looks like very similar to the SSS story. Now, when we introduce Vs using the gravity inner product, it inserts S transformations in the propagation of a bulk toroidal slice. So this was a gadget that we get from this vertex that we can insert onto a torus. And it turns out with the right choice of Vs, corresponds to either simple propagation with K inverse, or first a modular S transformation and then propagation by K inverse. And in particular, we can insert an arbitrary number of these gadgets into the propagation of a bulk torus. In the h bar going to 0 limit, the sum over all these insertions actually gives you a projector onto S equals to 1. And that is exactly implementing modular invariance, or S modular invariance. To get the full SL2Z modular invariance, we have to remember that we actually summed over T transforms by hand. So combined, we get the full SL2Z sum. And interestingly, these new wormholes will produce Seifert manifolds that are known to be needed to cure the negative density of states that would arise from the SL2Z sum over BTC black holes. Okay, now I want to explain the sum over all manifolds and the Schwinger-Dyson equation. So I want to begin by explaining how surgery arises in our model. It arises when we average over tensor model loops. So anytime we see a loop in the tensor model, the triple line Feynman rules tells us to sum over the indices that run along there, and that's the sum over the CFT spectrum. But that means that we'll insert that into the matrix integral, which replaces it to leading order with a Carty density. We've sort of seen this sum over modular S matrix elements and Wilson loops before when we discussed the BTC black hole. What it's doing is it's implementing toroidal surgery. It takes a torus neighborhood, a solid torus neighborhood of this red loop, and removes the solid torus, but glues it back in with the S twist. It glues in the dual torus. But what this does is it removes the hole here, it removes the non-contractible cycle. And it turns out this is implementing the Moore-Seiberg relations. What I mean is that in this particular diagram, what I've done is glue together two 6J manifolds. This is one 6J symbol, and this is another 6J symbol. The gluing is a multiplication. Thank you. The gluing is a kind of multiplication. And we multiply two 6Js together, and the surgery tells us that multiplying two 6Js gives us a pillow. But the pillow was a delta function. So this statement is saying that the 6J symbol is orthogonal in some sense. Now, there's another important consequence of surgery, which is that it produces braids. So we can glue together two 6J manifolds, but with a relative rotation, so that, as you can see, there's here an undercrossing and then an overcrossing. Now, the surgery removes this red loop, so the end result of this gluing is just to produce braided lines. When we close the braids, we produce links, which are like disconnected pieces of knots. And there's a theorem by Lickrish that we can build all three manifolds if I can produce an arbitrary link inside a reference three manifold. There's a generalization, so Lickrish proved it for closed manifolds. It also works for manifolds with boundaries. Now, I want to say the sort of final, very important consequence of surgery, which is that we get many tensor model diagrams with the same topology, but weighted by different powers of h bar. So the structure of our observables in the tensor model is we insert someCijks, and we can organize the diagrams into a sum over manifolds M. There's a 3D gravity partition function, but it's multiplied by overall sort of coefficient function f that just collects together all the powers of h bar. This is an e to the minus c expansion because the gravity part goes like e to the minus c to the volume. This is a statement of the volume conjecture that applies to Virasoro TQFT. But to match with gravity, we really want this coefficient function to go to 1 as h bar goes to 0. So we can check this conjecture by assuming it's true and then plugging it in to the h bar going to 0 limit of the Schwinger-Dyson equations. The Schwinger-Dyson equations are a set of recursion relations for the correlators of the theory, and we want to check the ansatz is correct. So, for example, here, one particular Schwinger-Dyson equation says that the full two-point function ofCijks, which means that we can insert any manifold in here, in this blob, with two boundaries, is the full two-point function, should be equal to these two objects, the difference of these two objects. One of them involves a blob here that is the full four-point function. And here, again, there's a full four-point function that sums over all three manifolds with four boundaries. If we zoom in on a particular manifold on the left-hand side here, say this manifold that is S2 times interval with three Wilson lines, then we get a finite counting problem. The counting problem is just to show that if I consider all three manifolds I can put in this blob, so that when it connects to the pillow graph, it reproduces this manifold. If I count all those manifolds, and then I also count all the manifolds that go into this blob, and reproduces the same manifold here on the left-hand side, I need the difference of those two sets, or number of elements in those sets, to be 1. So that's a mathematical problem we haven't solved, but hopefully some kind of generalization of topological recursion might give us a solution to it. I want to close with some final remarks. So we've shown that the topological expansion of 3D gravity arises from a random ensemble of approximate CFTs. This sum over topologies implements bootstrap constraints order by order in the e to the minus c expansion. Now, a successful non-perturbative completion of this sum would solve the bootstrap equations exactly and land us in the space of exact CFTs. We don't know how to do this, but we expect, by analogy with SSS, is e to the minus e to c question. So it's doubly non-perturbative. Now, the matrix model sums over a simpler class of manifolds, so perhaps we could start by understanding the non-perturbative completion of that sum. So I'll just end with an Outlook slide, but I'll just let you guys look at that, and please feel free to ask any questions.
Thank you very much for that very nice talk. Questions?
In your matrix model, have you verified that the integral over the OPE coefficients converges?
Sorry, so you're not thinking about summing of the diagrams. You're saying the integral of the OP coefficients, you mean the averaging of the OP coefficients. So that just gives you, for example, the S2 times interval wormhole picture. That just gives you the C0 function, the 3-point function of Liouville's theory. So maybe I'm not answering your question correctly. Like, what do you mean by convergence in this context?
You have a partition function,
yeah,
which is an integral over the C's, and you have a potential that is quartic in the C's.
Yeah.
So the question is, does the integral converge?
Well, the question whether the integral converge is this non-perturbative question that we don't know the answer to. So any question about summing over all diagrams, I can't give you the answer to. But if you ask me any question about a particular diagram, I can just tell you the answer for that diagram. For the tensor model, it comes from TQFT. For the matrix model, it comes from an analog of SSS. But yeah, that's an interesting question that certainly will be future work, yeah.
Yeah, Alex.
Yeah, thanks for the nice talk. Can you go back to your slide where you had the input and then output?
Sure.
Yeah, there it was.
Sorry.
Yeah, so I don't quite understand why you're treating the 1-point function of rho on the disk as kind of an independent input that you need to put into the model, different than the square of modular invariance, because the Cardy formula is an output of modular invariance itself.
Well, not in, I mean, you could think of it that way in the conventional way we derive the Cardy formula, but here we're not starting with modular invariance, right? Are you saying you want to do alternative? You want to do alternative kind of organization of this? I mean, in this story, we don't impose modular invariance from the start, right?
Indeed, but your potential term will impose it in the small h bar limit. So the fact that rho disk becomes Cardy will be already imposed in your model in the small h bar limit.
Okay,
even if you hadn't put in it by hand to start.
Yeah, maybe let me say differently. Maybe what we're really doing is we're just choosing to expand around the Cardy density. So maybe that's a choice of a particular place to expand about, rather than an input. Maybe it's not this input on the same level as the inner product here. Yeah, it's just where we're starting.
Yes.
Hi. So in your formula at the end where you wrote sum over m z graph times f of m h bar, it kind of looks like sum over saddle points times the f kind of looks like a sum over loop contributions. Could it be that like when you add matter and so on, that you could actually interpret this f as some loop contributions to the gravitational partition function, or should I think of the loop contributions as being inside z graph?
Well, as far as I understand what you say, I mean, the z gravity itself contains the one loop part of the gravity partition function. So for me, yeah, I would think that that's already in the z graph.
I guess the confusing thing is that you might expect that semi-classical gravity, is some sort of ensemble, right? So you might expect that at some level you should be reproducing at leading order in e to the minus c the actual gravity partition function. Why is this extra thing there?
Well, it's because h bar is not a parameter of 3D gravity. So we wanted to take h bar going to zero limit, and we produce gravity in that limit. And that's sort of clear from the definition of the model because we wanted to implement the bootstrap equations. And I said at the very beginning that 3D gravity is just implementing the bootstrap equation. But then I cheated, right? I cheated by smearing the constraints. So that's why we didn't land on 3D gravity as found in h bar. But almost by definition, it should land there when h bar goes to 0. And the question is whether this f goes to 1 in that limit. So the f has to do with this combinatorics of these pictures that I'm drawing here.
Kumron.
Very nice talk, very inspiring. In analogy with the case of JT gravity, where the ensemble can be interpreted in the regular large N duality in terms of computation of Wilson lines in higher dimensional theory, I wonder whether this could be related to the following picture, where you consider, let's say, 60 theories with 1, 0 supersymmetry, and they have surface operators. So there will be an ensemble, so the analog of the ensemble averaging will be computation of the correlation functions for the surface operators in this theory. Large N duality will tell you this should be related to something involving holographic M-theory dual, which will involve M2 branes stretched between these surface operators. Now, if this could be related to what you are doing, the question would be in that context, we don't have a natural sum over M2 brane topologies. There's no natural coupling constant and all that. So my question to you is, what's your analog of coupling constants with summing over manifolds?
I don't know. I suppose in this case, e to the minus c was the sort of parameter that we're expanding in. So I would, I don't know the details of what you were just saying, but I would look for the analog of e to the minus c, the analog of that parameter.
So there's no analog of genus or something. So what is your topology in doing that, in other words? What's the analog of the invariant which characterizes different manifolds?
Well, there was sort of an analog of the genus, like in the explanation of this kind of manifold, which when we attach a circle to this 2D manifold, the 2D sum was a genus expansion. And in the double-scaled sort of SSS interpretation, the expansion parameter has to do with genus. But here, we've replaced that parameter with e to the minus c, because e to the minus c is the level spacing according to our density. So the e to the minus c is sort of playing a role of the genus parameter here. But I agree with you, it doesn't sound like a geometric topological invariant. So, yeah.
Yeah.
Does the tensor part of your model distinguish between hyperbolic three manifolds and non-hyperbolic three manifolds, or are they treated on the same footing?
Well, the tensor part reproduces Virasoro TQFT, and Virasoro TQFT is not well defined on non-hyperbolic manifolds. It gives infinities. So that was one of the loose ends. We have to somehow renormalize or get rid of these infinities.
Because that would be a divergence on the level of a single diagram if you compute a non-hyperbolic.
Yes, yes. So we would have to hope for some kind of renormalization or cancellation.
Thank you.
There's a question online.
There's a question from Ofra Haroni. He's asking, why do you use the same H-bar for the crossing and modular invariance constraints? Shouldn't you have independent couplings in the bulk for them?
Well, I suppose so the thing is, there are many choices one makes in this model, so I'm not sure what the advantage of that choice would be. I have a very naive answer, this choice worked. Yeah, so I don't have any better answer for that, yeah.
Okay, let's thank Gabriel again.